Hello everyone. Today we shall discuss chapter 9 of class 9 and the chapter is gravitation. First of all, we'll try to learn what is in gravitation and we'll learn it by line what is the meaning of this one, right? First of all, we see what is given in this chapter, that is gravitation. We have learned about the motion of objects and force as the cause of motion. We have learned that a force is needed to change the speed or direction of motion of an object. We always observe that an object dropped from a height falls towards the earth. We know that all the planets go around the sun. The moon goes around the earth. In all these cases, there must be some force acting on the objects, the planets, and on the moon. Isaac Newton would grasp that the same force is responsible for all the force is called the gravitational force. In this chapter, we shall learn about gravitation and the universal law of gravitation. We shall discuss the motion of objects under the influence of gravitational forces on the earth. We shall study how the weight of a body varies from place to place. We shall also discuss the conditions for objects to float in liquids. First, we will learn about gravitation. We know that the moon goes around the earth. An object, when thrown upwards, reaches a certain height and then falls downward. It is said that when Newton was sitting under a tree, an apple fell on him. The fall of the fall of the apple made Newton start thinking. He thought that if the earth can attract an apple, can it not attract the moon? Is the force the same in both cases? He conjectured that the same type of force is responsible in both the cases. He argued that at each point of its orbit, the moon falls toward the earth instead of going off in a straight line. So it must be attracted by the earth, but we do not really see the moon falling towards the earth. Let us try to understand the motion of the moon by recalling activity 7.1. Here you see there is an activity, this one, right? Take a piece of thread, take a small stone at one end, hold the other end of the thread and wind it around as shown in figure 9.1. Note the motion of the stone. Release the thread. Again, note the direction of motion of the stone. Before the thread is released, the stone moves in a circular path to a certain speed and changes direction at every point. The change in direction involves change in velocity or acceleration. The force that causes this acceleration and keeps the body moving along the circular path is acting towards the center. This force is called the centripetal, meaning center-seeking force. Let us understand this one. How to understand this one, right? First of all, we will learn how it goes. Actually, what happens in case of actually what happens in case of circular motion? So in circular motion, what we get that in this type of, suppose this is a circle, we are taking a circle here. Let us take a circle. Right? What happened in this case that this is what we call, this is the center and this is the, suppose, the string, and we are there is a particle here and the particle is in this way, it is going on, right? And you remember that what you get, that there is a force or displacement in this direction and there is a force of attraction towards the center of this circle, and this is what we call it as centripetal force. This is called, call it as centripetal force. Centripetal force. Centripetal force is towards the center of the circle. Centripetal force, right? And this is what we call it as the direction of this particle at this moment. And you see, this is always 90 degree. This is 90 degree, right? It is always 90 degree to the radius of this circle, right? And centripetal force is always towards the center of the circle. That is the centripetal force. We learn about it later on, that what is that centripetal force and what is the value of this centripetal force, right? Now you can understand that this is a centripetal force and this is the direction of this particle at any moment. Suppose the particle is at this point, again you can see that this is the centripetal force and the particle moves in this direction. At that point, at that instant of time, the angle between them is 90 degree. Again here, again you see this is 90 degree, right? In this you can say that at every instant of time, the velocity is changing. Though if it is constant speed, its velocity is changing because the direction is changing. That means velocity is also changing, right? Now we learn next what is given, right? You see this one, right? Gravitation, right? That is, this force is called centripetal force, means center seeking force, right? This is center seeking force. In the absence of this force, the stone falls off along a straight line. The straight line will be tangent to a circle, right? What happens in this case if we release, here you see, if we cut this thread, it will always go along the tangent. What is the meaning of tangent? Tangent means, suppose this is a circle. Suppose this, we have taken a circle here, right? We have taken a circle here, and when we release this one, that is this one, if we release, this, this is the center. If we cut this thread, this object will move perpendicular, or what we call is tangentially to that. Tangential means 90 degree, 90 degree to radius. At this moment, this particular move in this direction. If the object is here, suppose the object is here, then it will move tangentially. Tangentially means 90 degree to the radius. That is tangentially. It is 90 degree. 90 degree to the radius. That is what is called tangentially. This is called tangent, or tangentially it will goes off along this direction, right? That is why what we call as tangential, right? Next one is, that is, in the absence of this force, the stone flies off along a straight line, that is tangentially, or what we call naturally to the radius. This straight line will be a tangent to the circular path. This is tangent to the circular path. I already told you that this is tangent means this one. This is tangent means this one. This is the tangent to the circle. That means it is 90 to the radius. In this way, this is 90, this is 90, right? A straight line that meets the circle at one and only one point is called the tangent to the circle. A straight line ABC is a tangent to the circle at the point B. That means it is 90 degree, right? That is tangent to the circle. That is tangent to the circle, right? The motion of the moon, here is, you can see, right? In this way, you can find out the how to find the tangent to a circle. Now we learn about the universal law of gravitation, right? Now we learn about the universal law of gravitation. Let us find out what is that. right? That means we have found that this is tangential to that of the circle. Tangent means, again I am telling you, this is the tangent. Suppose this is a circle. I am telling you how to find this one. That is, suppose this is right. I'll find this one. Find, right. This is what we call a tangent to the circle. Now we learn about this. Here you see that is it the motion of the moon around the earth is due to centripetal force. Let us again go to this one. That is, we are getting that, right. The motion of the moon, you can find here that the motion of the moon around the earth is due to centripetal force. The centripetal force is provided by the force of attraction of the earth, right. If there is no such force, the moon would pursue a uniform straight line motion, right. It is seen that, right. That means the motion of the moon around the earth is due to the centripetal force. The centripetal force is provided by the force of attraction of the earth. If there is no such force, the moon would pursue a uniform straight line motion. It is seen that the falling apple, it is seen that the falling apple is attracted towards the earth. Does the apple attract the earth? If so, we do not see the earth moving towards an apple. Why? According to the third law of motion, the apple does not attract the earth. But according to the second law of motion, for a given force, acceleration is inversely proportional to the mass of an object. We know that acceleration is proportional to the inversely proportional to the mass of the object. How? Let us find out how this is given. There, according to second law of motion, for a given force, acceleration is inversely proportional to the mass of the object. How it is found? We know that in this case that F is equal to ma. F is equal to mass at acceleration, right? Or you can write F is equal to A by m. Therefore, acceleration is inversely proportional to the mass of the object. We find before that also, right. Acceleration is inversely proportional to the mass of the object. To remember this equation, right, here you can see that acceleration is inversely proportional to the mass of the object, right. Now you can see that the mass of an apple is in our solar system. In our solar system, all the now you can see that according to the second law of motion, for a given force, acceleration is inversely proportional to the mass of an object. The mass of an apple is negligibly small compared to that of Earth, so we do not see the Earth moving towards the apple. Extend the same argument for why the Earth does not move towards the moon. In our solar system, all the planets go around the sun. By arguing the same, we can say that there exists a force between the sun and the planets. From the above facts, Newton concluded that not only does the earth attract an apple and the moon, but all the objects in the universe attract each other. This force of attraction between objects is called the gravitational force. This force of attraction between objects is called the gravitational force. Now we'll find what is the meaning of universal law of gravitation. You'll find here universal law of gravitation. If here you see that every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. This force is along the line joining the center of two objects. What is the meaning of this one? Suppose there are two particles, this particle A and particle B. This is the center of A, this is the center of B. If we join a line between the centers, we get the distance as D. Therefore, if what we get, the force is equal to the product of the mass. Suppose the mass of this object A is capital M and the mass of small b is small m and the distance between the d, then we can find that the gravitational force between two uniform objects is directed along the line joining their center. Therefore, we get the value F is equal to capital G, capital M, small m by d square, where G is the universal gravitational constant, right? Here we'll find what is that next one. We find the gravitational force between two uniform objects is directed along the line joining their centers. Here we find that let the two objects A and B of masses capital M and small m lie at a distance d from each other as shown in figure 9.2. Let the force of attraction between the two objects F. According to the universal law of gravitation, the force between two objects is directly proportional to the product of their masses, that is capital F is directly proportional to capital M is small m. And the force between the two objects is inversely proportional to the square of the distance between them, that is F is directly proportional to 1 by d square. That is combining equation 1, 10.1 and 10.2, get F is directly proportional to capital M is 1 m by d square or F equal to capital G, capital M is 1 by d square, where capital G is the constant of proportionality and is called the universal gravitational constant. If you remember that this is the universal gravitational constant, right? This is the universal gravitational constant, where G is called the constant of proportionality and is called the universal gravitational constant. That is, by multiplying crosswise gives F d square equal to capital G, capital M by small m. That is the value of force here, right? Have you remember this one also, right? Now we'll find different things. That next one, let us then okay. Now we'll find this one, how we can got this one. Let us find out again. Suppose there is a force here. Suppose there is a force we got here. There is a force. There are two objects. One is capital M. The mass of this object is capital M, and there is another body that is small m. And suppose this is the center of this point, and this is the center. If you join the center to center, that is the distance between them, small d, right? And if there is a force of attraction, we know that the force is directly proportional to the product, means multiplication of mass, that is capital M into small m. This is number one equation. And number two is that force is inversely proportional to the square of the distance between them, 1 by d square. Therefore, what we get that F is directly proportional to capital M small m by d square, right? And if we write F is equal to, then we have to put a gravitational constant capital G, capital M by small m by d square. This is the formula for gravitational force. The capital F equal to capital G, capital M, small m by d square, right? And G is called the universal gravitational constant. Capital G is known as universal gravitational constant. Universal gravitational constant. Gravitational constant. This is what we call it as universal gravitational constant, right? Okay, this is called it that where g is the constant of proportionality and is called the universal gravitational constant. By multiplying crosswise, we get equation 9.4 that capital D into d f into d square equal to capital G capital M into small m. Right. Now we'll find the next one that capital G we can write here as capital G equal to f d square by capital M into small m. The SI unit of G can be obtained. The SI unit of G can be obtained. The SI unit of G can be obtained by substituting the units of force, distance, and mass in equation 9.5, right? As Newton by 1 meter square per kg. The value of G was found out by Henry Cavendish 1731 to 1810 by using a sensitive balance. The accepted value of G is 6.673 in 10 to minus 11 Newton meter square per kg square. You remember this one also, right? Because the value of G is 6.673 into 10 to minus 11 Newton meter square per kg square. We know that there exists a force of attraction between any two objects. Compute the value of this force between you and your friend sitting close by. Conclude that how you do not experience this force. The law of universal gravitational force. And yet the law is universal in the sense that it is applicable to all bodies, whether the bodies are big or small, whether they are celestial or terrestrial. Inverse square saying that inverse square Inverse square saying that f is inversely proportional to the square of the distance d means, for example, that if d gets bigger or by factor 6, f becomes 1 by 36 square times smaller, right? The f becomes 1 by 36 times smaller, right? The mass of now we can find there are various examples here. Examples we'll do it in later on, right? Now we'll find, suppose this one there is an example, let us do it. The mass of an earth is the mass of the earth is a 6 × 10 minus 24 kg. Mass of the moon is 1.8 into 22 kg. The distance between the earth and the distance earth and moon is given that 3.84 to the 8 meter and g 6.7 into minus 11 newton per meter square per kg square. Therefore, we find the value of capital F as capital G, capital M is small m by d square. That is capital value of capital G is 6.7 into minus 11 newton meter square per kg square, and the mass of this earth is 6 into 10 to 24 kg, and mass of moon is 74 into 10 to 22 kg. And the distance between the 3.84 to the 8 meter. If we calculate, we get the value 2.02 10 to 20 Newton. Thus, the force exerted by the earth on the moon is 2.02 into 10 to the power 20 Newton. Next question is state the universal law of gravitation. Write the formula to find the magnitude of the gravitational force between the earth and the object on the surface of the earth. Importance of the universal law of gravitation. The universal law of gravitation successfully explained several phenomena which were believed to be unconnected. The force that binds us to the earth, the motion of the moon around the earth, the motion of planets around the sun, and the tides due to the moon and the sun. The universal law of gravitation successfully explains several phenomena which are believed to be unconnected. The force that binds us to the earth, the motion of the moon around the earth, the motion of planets around the sun, and the tides with the moon and the sun. Now we'll explain about what is the meaning of free fall, right? Let us try to understand the meaning of free fall by performing these activities. Take a stone, throw it upwards, it reaches a certain height, and then it starts falling down. We have learned that the earth attracts towards the earth. This is due to the gravitational force. Whenever the objects fall toward the earth under this force alone, we say that the objects are in free fall. Is there any free fall? Is there any change in the velocity of falling objects? While falling, there is no change in the direction of motion of the objects, but due to the Earth's attraction, there will be a change in the magnitude of the velocity. Any change in the velocity involves acceleration. Whenever an object falls toward the earth, an acceleration is involved. This acceleration is due to the earth's gravitational force. Therefore, this acceleration is called acceleration due to the gravitational force of the earth or acceleration due to gravity. It is not denoted by small g. The unit of small g is the same as that of the acceleration, that is meter per second square. We know from second law of motion that a force is the product of mass and acceleration. Let the mass of the stone in activity 9.2 pm. We already know that there is the acceleration involved in falling objects due to the gravitational force and is noted by g. Therefore, the magnitude of the gravitational force F will be equal to the product of mass and acceleration to the gravitational force, that is F equal to m into g, right? Therefore, the magnitude of the gravitational force F will be equal to the product of the mass and acceleration to the gravitational force, that is F equal to m into g. And we know that mg equal to, that is, there is a force, and if mg equal to capital G mm by d square, therefore we get the value g as this one. If we get the value g as capital small g is equal to, we get the value of this one, that small g is equal to capital G capital M by small d square. That is the value. Where capital M is the mass of the earth, small d is the distance between the object and the earth. Let the object be on or near the surface of earth. And let an object be Let the object be on or near the surface of Earth. The distance d in equation 9.7 will be equal to r, the radius of the Earth. Thus, for objects on or near the surface of the Earth, mg equal to capital G m by r square, or you get the value g is equal to capital G m by r square. Right? Then you get this value. Now, what we find that the Earth is not a perfect sphere. As the radius of the Earth increases from the poles to the equator, the value of g becomes greater at the poles than at the equator, right? Remember that the value of g increases at the poles, increases, it becomes greater at the poles than at the equator. For most calculation, we can take g to be more or less constant on or near the earth. But for objects far from the earth, the acceleration due to gravitational force of earth is given by equation 9.7. This one, right? The capital G, capital M by G square. To calculate the value of small g, we should put the values of capital G, capital M, and R in equation 9.9. Namely, the universal gravitational constant capital G 6.7 to minus 11 Newton meter square per a square. Mass of the Earth is 6 into 10 power 24 kg, and radius of Earth 6.4 into 10 power 6 meter. If we put the value, the value of g will be 9.8 meter per second square. Thus, the value of acceleration due to gravity of the Earth is 9.8 meter per second square. This is the value. 9.8 meter per second square. The value of g is 9.8 meter per second square. Motion of objects under the influence of gravitational force. Motion. Motion of objects under the influence of gravitational force of the earth. Let us do an activity to understand whether all objects, hollow or solid, big or small, will fall from a height at the same rate. Take a sheet of paper and a stone, drop them simultaneously from the first floor of a building. Observe whether both of them reach the ground simultaneously. We said the paper reaches the ground little later than the stone. This happens because of air resistance. Air offers a resistance to the friction of the motion to the falling objects. The resistance offered by air to the paper is more than the resistance offered to the stone. If we do the experiment in a glass jar from which air has been sucked out, the paper and the stone would fall at the same rate. That is, in vacuum, all the objects will fall with the same speed, right? Here we find that we know that an object experiences acceleration during free fall. From equation 9.9, this acceleration experienced by an object is independent of its mass. This means that all the objects, hollow or solid, big or small, should fall at the same rate. According to a story, Galileo dropped different objects from the top of Leaning Tower of Pisa in Italy to prove the same. As g is constant at the r, all the equations for the uniformly accelerated motion of objects become valid with acceleration a replaced by g. The equation is equal to u plus at is equal to ut plus half at square equal to v square v square plus 2a, where u and v are the initial and final velocities and this is the distance covered in time t. In applying these equations, we will take acceleration a to be positive when it is in the direction of the velocity, that is, in the direction of motion. The acceleration a will be taken as negative when it opposes the motion, right? Now we'll find what is given. The next one is this one. Motion of objects under the influence of gravitational force of earth, right? We have already explained this one, right? Next, what is the question? That is mass. Now we find the difference between mass and weight. We have learned in the previous chapter that the mass of an object is the measure of its inertia. We have also learned that the greater the mass, greater is the inertia. It remains the same whether the object is on the earth, the moon, or even in outer space. That the mass of an object is constant and does not change from place to place. What is weight? Weight, we know that earth attracts every object with a certain force, and this force depends on the mass of the object and the acceleration due to gravity. The weight on an object is the force with which it is attracted towards Earth. We know that F equal to ma, and therefore the force, you can say that it is the force. We know that F equal to mg, that is the force or weight, and this force is the weight. The weight is equal to, or you can say weight equal to m into g. Weight, this is weight. Weight equal to m into g. The force of attraction of the Earth. The force of attraction of the earth on an object is known as the weight of the object. It is denoted by W. Substituting the same in equation 9.14, we have W equal to m into g. That is the weight. As the weight of an object is the force with which it is attracted towards the earth, the SI unit of weight is the same as that of force, that is Newton. The weight is a force acting vertically downwards. It has both magnitude and direction. Therefore, it is a vector quantity, right? We have learned that the value of g is constant at a given place. Therefore, at a given place, the weight of an object is directly proportional to the mass m of the object. That is, W is directly proportional to m. It is due to this reason that at a given place we can see that the weight of an object is a measure of its mass. The mass of an object remains the same everywhere, that is on the earth or at any planet, whereas its weight depends on its location because g depends on location. Weight of an object on the moon. What is the weight of an object on the moon? We have learned that the weight of an object on the earth is the force with which the earth attracts the object. In the same way, the weight of an object on the moon is the force with which the moon attracts that object. The mass of the moon is also less. The mass of the moon is less than that of the earth. Due to this, the moon exerts lesser force of attraction on objects. Let the mass of an object be m. Let its weight of the moon be Wm. Let the mass of the moon be capital M small m and its radius be Rm. By applying the universal law of gravitation, the weight of the object on the moon will be capital G, capital M, the mass of the moon, mass of the object by Rm, radius of moon whole square, and the weight of the same object on the earth be We, the mass of the earth be m and its radius r, then we get the value We is equal to capital G, capital M, small m by r square. Substituting the values from 10.1 0 in equation 9.16, that is this value W equal to capital G capital M small m by R square. Substituting the values of from table 10.1 in equation 9.16. Here we get Wm equal to capital G, the value of mass of the moon is 7.3 10 to the 2 kg, and this is the mass of the object 1.74 10 power minus 6 10 to the 6 meter square, and mass of the moon we get as this one, that is m or may equal to 2.431 10 to the power 10 g into m, and weight of earth is 1.474 10 to the power 11 g into m. Dividing this equation, we get the value mm will cut, that is Wm by We 2.4 31 10 to the power 10 by 1.474 10 to the power 11, and W by We is equal to 0.165, that is equal to 1 by 6. That is weight of the object on the moon, and weight of the object on the earth, that is weight of the object on the moon is equal to 1/6 is weight on the earth. That is the value we get, right? That is weight of the moon will be always 1 by 6 part. The weight of the moon, that is the weight of the moon on the moon, weight of the object is 1 by 6 its weight on the earth, right? That is value we got it, right? Now what we find in the next page, that is this one, and of the net force in a particular direction, thrust and the force there 1/6 of the mass. Now in the base value thrust and pressure. What is the meaning of thrust and pressure? Have you ever wondered why a camel can run in a desert easily, why an army tank weighing more than 1,000 tons rests upon a continuous chain, why a truck or a motor bus has a wider tires, why cutting tools have salvages? In order to address these questions and understand the phenomenon involved, it helps to introduce the concepts of the net force in a particular direction, that is thrust. Net force in a particular direction is thrust, right? That is net force in a particular direction, we call it as thrust. Net force in a particular direction is called thrust, and the force per unit area pressure acting on the object concerned, that is force and pressure, right? Pressure. Let us try to understand the meanings of thrust and pressure by considering the following situations. Situation 1. What is that situation 1? Situation 1 is Situation 1 is, let us try to understand the meanings of the thrust and pressure by considering the following situations. If you wish to fix a poster on a bulletin board, as shown in 9.3, to do this task, you will have to press the drawing pins with your thumb. To apply a force on the surface area of the head of the pin, the force is directed perpendicular to the surface of the board. This force acts on a smaller area at the tip of the pin. In situation 2, you stand on the loose sand. Your feet go deep into the sand. Now lie down on the sand. You will find that your body will not go that deep in the sand. In both the cases, what is exerted on the sand is the weight of your body. You have learned that the weight is a force acting vertically downwards. Here the force is acting perpendicular to the surface. Here the force is acting perpendicular to the surface of the sand. The force acting on the object perpendicular to the surface is called thrust. There is the definition: the force acting on an object perpendicular to the surface is called the thrust. When you stand on the loose sand, the force is, that is, the weight of your body is acting on an area equal to the area of your feet. When you lie down, the same force acts on an area equal to the contact force of your whole body, which is larger than the area of your foot. Thus, the effects of forces of the same magnitude on different areas are different. There, this thing we have to remember, that there's the effect. What is that? Thus, the effect of forces of the same magnitude on different areas are different. In the above cases, thrust is the same, but effects are different. Therefore, the effects of thrust depends on the area on which it acts. The effect of thrust on sand is larger. The effect of thrust on sand is larger while they are standing than while lying. The result is, the thrust on unit area is called pressure. Pressure equal to thrust by area, or that is force by area. That is pressure equal to thrust by area is here pressure, that is pressure equal to thrust by area, right? Substituting the SI unit of thrust and area in equation, we get the SI unit of pressure as Newton per meter square. Newton per meter square. In honor of scientist Blaise Pascal, the SI unit of pressure is called Pascal, denoted by PA. Let us consider a numerical example to understand the effects of thrust acting on different areas. Let us find this one, how we get this one. Suppose here this is the block of wood. A block of wood is kept on a tabletop. The mass of the wooden block is 5 kg and its dimensions are 40 into 20 into 10, that is 40 into 20 into 10, and this is 40 into 20 into 10 centimeters, right? Let us find what happened now, right? Now here is it by the wooden block of the tabletop. It is made to lie on the tabletop with its dimension 20 into 10 and 40 into 60. That is 20 into 10 this is, and this is 40 into 20, right? Let us find that what is the difference. The mass of the wooden block 5 kg. The dimensions is this, and the weight of the wooden block applies a thrust on the tabletop, thrust equal to F equal to m into g. M is 5 kg and G is that 49 Newton. Area of the site, length in the breadth, that is 200 centimeters square. Therefore, pressure equal to force by area 49 Newton by 0.02, that is 2450 Newton meter square. When the block lies on its side and dimension 40 centimeter 20 centimeter, it exerts the same thrust force, that is area is equal to length into breadth, that is 0.08 meter square. Pressure equal to 49 by 0, that is 12.5 Newton per Newton meter square. Right? The pressure exerted by the side 20 into 10 centimeter is 2450 Newton per meter square, and the side and by the side 40 intensity is 612.5. That is, this pressure is more than this pressure. Thus, the same force acting on a smaller area exerts a larger pressure. Right? That is, if you remember, the same force acting the same force acting on a smaller area exerts a larger pressure and a smaller pressure on a larger area. This is the reason why a nail has a pointed tip, knives have sharp edges, and buildings have wide foundations. Right? Now we learn about pressure in fluids. Right? Pressure in fluids, we learn all these things. Pressure in fluids, we'll learn about that. Pressure in fluids. All liquids and gases are fluids. A solid exerts pressure on the surface due to its weight. Similarly, fluids have weight, and they also they also exert pressure on the base and walls of the container in which they are enclosed. Pressure exerted in any confined mass of liquid is transmitted undiminished in all directions. Now we learn about that the buoyancy. What is that buoyancy? Have you ever had a swimming pool in a swimming in a pool and felt lighter? Have you ever drawn water from a well and felt that the bucket of water is heavier when it is out of water? Have you ever wondered why a ship made of iron steel do not sink in the seawater, but while the same amount of iron steel in the form of a sheet would sink? These questions can be answered by taking buoyancy in consideration. Let us understand the meaning of buoyancy by doing an activity. Right here, there is an activity. Take an empty plastic bottle, close the mouth of the bottle with an airtight stopper, put it in a bucket filled with water. You see that the bottle floats. Push the bottle into the water. You will feel an upward force. Try to push it further down. You will find it difficult to push deeper and deeper. This indicates that water exerts a force on the bottle in the upward direction. The upward force exerted by water goes on increasing as the bottle is pushed deeper till it is completely immersed. Now the release the bottle, it bounces back to the surface. Does the force due to gravitational attraction on the earth act on this object? If so, why does the bottle stay immersed in water after it is released? How can you immerse the bottle in water? The force due to the gravitational attraction on the earth acts on the bottle in the downward direction, but the bottle is pulled downwards. But the water exerts an upward force on the bottle, thus the bottle is pushed upward. We have learned that the weight of an object is the force due to gravitational attraction of the earth. When the bottle is immersed, the upward force exerted by water on the bottle is greater than its weight. Therefore, it rises up and releases. To keep the bottle completely immersed, an upward force on the bottle due to water must be balanced. This can be achieved by an externally applied force acting downward. This force must be at least equal to the difference between the upward force and the weight of the bottle. The upward force exerted by water on the bottle is known as upthrust or buoyant force. This you have to remember that this one, that is the upward force exerted by the water on the bottle is known as the upthrust or buoyant force. In fact, all objects experience the force of buoyancy when they are immersed in a fluid. The magnitude of this buoyant force depends on the density of the liquid, right? That is, it is depending on the density of the liquid, right? Now, why objects flow? Why objects float or sink when placed on the surface of water? Let us do the following activities to arrive at an answer for the above question. Take a beaker filled with water, take an iron nail and place it on the surface of water. What observe? The nail sinks. The force due to the gravitational attraction of the earth on the iron nails pulls it downwards. There is an upthrust of water on the nail which pushes it upward, but the downward force acting on the nail is greater than the upthrust of the water on the nail, so it sinks. Take a beaker filled with water, take a piece of cork and iron nail of equal mass, put them on the surface water, what happens? The cork floats while the nails sink. This happens because of the difference in their density. The density of a substance is defined as the mass per unit volume. That you have to remember the density. What is that? Density of an object. Here see, the density of a substance is defined as the mass per unit volume. The density of a cork is less than the density of water. It means that the upthrust of water on the cork is greater than the weight of the cork, so it floats. The density of an iron nail is more than the density of water. This means that the upthrust of water on the iron nail is less than the weight of the nail, so it sinks. Therefore, objects of density less than that of a liquid float on liquid. Right? Therefore, the objects of greater density than that of a liquid will sink in the liquid. The objects of density greater than that of the liquid sinks in the liquid. Right? Why is it difficult to hold a school bag having a school bag having Why is it difficult to hold a school bag having a strap made of a thin and strong string? What do you mean by buoyancy? Why does an object float or sink when placed on the surface of water? Now we will learn about Archimedes' principle, right? What is that Archimedes' principle? Take a piece of stone and tie it to one end of a rubber string or a spring balance. Suspend the stone by holding the balance and the string as shown in figure 9.6a in this way, right? Note the elongation of the string or the reading of the spring balance due to the weight of the stone. Now slowly dip the stone in the water in a container shown in figure 9.6b in this way, right? What happens in this case, right? When a body is immersed fully, this is the when a body is immersed fully. Observe what happens to elongation of the string or the reading of the balance. You will find that the elongation of the string or the reading of the balance decreases as the stone is gradually lowered in the water. However, no further change is observed once the stone gets fully immersed in the water. What do you infer from the decrease in the extension of the string or the reading of the spring balance? We know that the elongation produced in the string or the spring balance is due to the weight of the stone. Since the extension decreases once the stone is lowered in water, this means that the sum force acts on the stone in upward direction. As a result, the net force on the string decreases and hence the elongation also decreases. I discussed earlier, this upward force exerted by water is known as force of the buoyancy. What is the magnitude of the buoyant force experienced by a body? Is it the same in all fluids for a given body? Do all bodies in a given fluid experience the same buoyant force? The answer to this question is explained in Archimedes' principle and stated as follows. When a body is immersed fully or partially in a liquid fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. That is important. Now we can explain. Now can you explain why a further decrease in the elongation of the string was not observed in fluid 9.7 as the stone was fully immersed in water? Archimedes was a Greek scientist. Archimedes was a Greek scientist. He discovered the principle subsequently named after him after noticing that water in a bathtub overflowed when he stepped into it. He ran through the streets shouting, Eureka, which means I have got it. This knowledge helped him to determine the purity of the gold in the crown made for the king. His work in the field of geometry and mechanics made him famous. His understanding of levers, pulleys, wheels, and axles helped the Greek army in its war with Roman army. Right? Archimedes' principle has many applications. It is used in designing ships and submarines. Lactometers, which are used to determine the purity of a sample of milk, and hydrometers used for determining the density of liquids are based on this principle. Right? These are the various activities. What we have learned. The law of gravitation states that the force of attraction between any two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. This law applies to objects anywhere in the universe. Such a law is said to be universal. Gravitation is a weak force unless large masses are involved. The force of gravity decreases with altitude. It also varies on the surface of the earth. decreasing from poles to the equator. The weight of a body is the force with which the earth attracts it. The weight is equal to the product of mass and acceleration due to gravity. The weight may vary from place to place, but mass stays constant. All objects experience a force of buoyancy when they are immersed in a fluid. Objects having density less than that of liquid in which they are immersed float on the surface of the liquid. If the density of the object is more than the density of the liquid in which it is immersed, then it sinks in the liquid. Right? These are the various activities we have done and we have learned about the gravitational force. Right? Thank you everybody for watching this video.